So, good afternoon, everybody. My video is not working. That's why I just stopped my video here and you can just see my picture. Probably the chat's not going to work, but you can unmute yourself and ask questions if you want. I just want to show you some things here before we start, before we continue on the lecture about mortality. On this lecture here about the sources of demographic information, I just want to show you that I update, instead of showing the questionnaire for the 2010 census, I just put here the one that was just used now for the 2020 census. And so this first portion here of the questionnaire, you have this basic information that you ask how many people living in the household, and the census date is all in reference to April 1st, how many people are living in that household on April 1st. And just to be sure, if there were additional people staying there in April 1st that were not included here, we also ask this question. And the Census Bureau also asks if the house is owned or rented or occupied, and phone number if they need to get in touch with them again. And then the question to the person who is the head of the household, those same questions about name, sex, age, date of birth, just to confirm the age, and then ethnicity, about being Hispanic, and race. And we're going to talk more about the race ethnicity variables in the lecture about race ethnicity, where I show how this variable, how these questions changed over time, and how they were planning to actually combine race ethnicity questions, but they just kept them separated. And for the other individuals in the household, the same questions apply: name, sex, age, date of birth, ethnicity, and race. But it also asks if that person usually live or stay somewhere else, such as college students, people in the military. And it also asks for each one of the other people in the household, person 2, 3, 4, and so on, what's their relationship with the head of the household. So I updated these slides related to the chapter about the sources of demographic information. It's available in our website. In the last class, I mentioned to you some possible effects that the current pandemic might have on fertility rates. And we usually, when we hear informal conversations of people about the effects of the pandemic on fertility, people usually joke about it, saying that now that people are staying more at home, we would see an increase in fertility rate. But as I show you, based on previous information that we have from the approximate determinants of fertility, actually, the fact now that we have an economic recession, so that's this major economic change that affects change of people getting married, so decreases chance of people getting married because they don't have a stable life right now, and might actually increase the chances of people getting divorced. That might have a negative effect on fertility rates, and that's what has been already shown by preliminary results. So this is a news article from the week that was just published now on March 26th. And I just saw this, this article that was Professor Leticia Martelletto. She's a professor in the Sociology department at the University of Texas at Austin. And she just tweeted this, and I follow her and I saw that information. And in this specific extract here, it really shows, like, researchers Melissa Kearney and Philip Levine estimate that the pandemic will result in 300,000 to 500,000 fewer babies born in the US. Lockdowns and fear kept young people from meeting and marrying, and economic hardship discouraged many young couples from having kids. So it's exactly what that discussion we were having in the previous class when John Bongers proposed those approximate determinants of fertility, mentioned that there are socioeconomic factors, these big factors, that impact specific more proximate determinants that make people having more or less children. So exactly because of people being more at home in this case and having more economic hardship, unemployment is still high and so on, make people postpone marriage and make people postpone having children, right? So it's just an interesting, all these findings, they emphasize the importance of us knowing this previous knowledge that we have about demographic components, in this specific case, fertility, how previous knowledge, these previous theories, they help us understand what the current pandemic might result in terms of fertility and mortality. And also in the last class, I mentioned that in terms of mortality, we, of course, might see some effects of the pandemic on life expectancy. And I mentioned a specific case of some demographers, and specifically I saw the demographer is a Brazilian demographer. His name is Gabriel Borges. He is based in the Brazilian Census Bureau, or more specific, the Brazilian Institute of Geography and Statistics. And again, I follow him on Twitter, and that's where I saw his estimates, because all these things are not published, but he showed his estimates that life expectancy in Brazil might drop from 76 years of life on average to 73. So drop 3 years. And that's a huge amount, because that puts Brazil in the same level of other less developed countries, such as African countries and some Asian countries. And he specifically mentions Bangladesh. Okay, so just to emphasize that all these different theories that we have been discussing throughout the course, they are important for us to understand what the current pandemic might cause in terms of effects on mortality, effects on fertility, and also effects on migration, right? Because then you have all these closed borders right now by the government, by different governments across the world, and they might inhibit migration as well, both international, but also internal migration. So we saw in the previous class, standardization, which is a technique in which we learn how to get crude death rates from 2 different countries, make some corrections in one of them, using the other one as the standard population, in order to be able to compare crude death rates of 2 countries that have different age structures. So that's pretty much standardization allows us to compare crude death rates of countries with different age structures, because we take into account age-specific death rates, right? In order to do this comparison, we estimate new crude death rate and are able to make the comparison of mortality in the US and Venezuela, instead of having the false idea that Venezuela has lower levels of mortality. It actually has higher levels of mortality when we take into account age structure. Another popular way to take into account age structure in order to create different measures, or measures that are comparable across countries or over time of populations that have been changed in age distribution, is the life table. That's a technique in which we can estimate life expectancy at birth, and that's what I'm going to explain it to you now. So today I am able to see the chat. If you want to ask a question through the chat, I can see it. So each day varies. That's this classroom, it's always a surprise. So one of the most important elegant measures of the mortality experiences of population is the life table. And actually, as I mentioned earlier in the semester, and also mentioned earlier in this lecture, the life table dates back to John Grant, who is known as being the father of demography, in his bills of mortality, where he estimates different chances of people dying by age, by sex, and by place of residence, in his case, urban and rural areas. And that's data from the 1600s from London. And demographers use the life tables to estimate, to determine life expectancy. And the interesting thing about life tables is that we can estimate life expectancy not only at birth, but at any age. Usually, we hear about life expectancy. Let's say, oh, Brazil has a life expectancy of 76 years. So it means that if we get a population and expose them to the mortality levels of the Brazilian population by age, those people will live on average 76 years since their birth. But life table provides much more than that. And one of the things is to say, okay, I had some chances of dying when I was young, but when I reached the age of 15, now that I passed through those chances, those risks of dying of earlier ages, and I survive up to age 15, I will have some bonus years of life. So that's what it's called, the life expectancy at any other age or at any other age group. Usually we estimate the life tables by age groups. Like the total fertility rate, the life table is in a synthetic or hypothetical measure. So just remember, it tells us how many years of life, on average, may a person expect to live if the person during his or her lifetime is subjected to the age-specific probabilities of dying of a particular country or population at a given time. What does it mean? When I get the age-specific mortality rates from a specific country, and then I make a calculation from the age-specific rates of dying, I estimate the probabilities of dying. It's for all these different age groups, for a specific population, specific time. And I calculate a life table, I'm saying that I'm doing a hypothetical exercise in which I expose people to those rates, but in reality, they are not going to experience those exactly rates. Because if I say, okay, someone who is 0 to 1 is expected to those mortality rates and mortality probabilities in that specific year. But when that baby reaches age 1 year from now, age 5 years from now, that baby is not going to be exposed to the probabilities of dying as they were measured in 2021. They will be exposed to the next years. So the exercise that we are doing here is the same exercise that we did with total fertility rate. We are saying that we have this hypothetical group of people that are exposed to those rates. In fertility, it tells us how many children on average women would have if they were exposed to those age-specific fertility rates. In mortality, how many years on average people would live if they were exposed to those age-specific mortality rates that we measure for a specific country in a specific year. Okay? So, here I'm going to show you an example for the US. Let's say that the population of the US in 2010 had a life expectancy of birth, or at birth, of 78.7 years. This means that if I get a group of people, cohort of persons, throughout the years of their life, and I subject them to those age-specific death rates, also symbolized by capital MXN, of the total population in the US in 2010, if I expose this group to the rates from the US in 2010, they will live on average 78.7 years. Okay? And these are some numbers, some examples for different parts of the world to show how these rates, they vary a lot. They vary not only across different areas, different regions in the world, different countries, but also by sex. As we have been talking throughout the semester, mortality is lower among women than among men. So women are expected to live longer than men on average. In all these examples here, we see exactly that, women living longer, which means that their mortality rates are lower, their risks of dying are lower than men. In the world, the life expectancy, the male life expectancy was around 69 years in 2013 and 73 for women. In more developed countries, higher, less developed countries, except China, lower than the world average. And just to show some extremes, Japan with really high life expectancies at birth, Lesotho and Sierra Leone, really low levels of life expectancy, which means really high levels of mortality. There are some limitations with the life expectancy at birth. And the life expectancy at birth is symbolized by this E0. So this E0 is a symbol for life expectancy at birth that we're going to use throughout all these discussions here. And we need to be aware that when we consider life expectancy at birth, infant mortality plays a very important role. So in some developing countries where infant mortality might be really high, such as in Lesotho and Sierra Leone, really high infant mortality rates make the life expectancy drop a lot. Right? So because life expectancy at birth is really affected by infant mortality. So when life expectancy at birth is low, a major reason is their very high infant mortality rate. What is the infant mortality rate? Is the number of children dying before reaching age 1 divided by the number of live births in a specific country in a specific year. That's the infant mortality rate. Children dying before reaching age 1. Sometimes when we are comparing data across countries, it might be interesting to not think of the life expectancy at birth as the model age at death. What is the mode? Mode is one one measure that we usually use in statistics. The mode is that number that's most observed for a specific indicator. So the mode of life expectancy would be the most probable age in which people up to which age people would live and die at that age. But when we have really high infant mortality rate in those countries, we should not think these numbers here as being the ages in which most people are dying. Age 42 among men in Lesotho and 45 among women in Lesotho, for example. Because maybe after people pass the risk of dying as babies before they reach age 1, what might happen is that they will have less chances of dying and they might pass and live longer than 42 and 45 in this example. So when countries have really high levels of infant mortality, you should not interpret the life expectancy at birth as the model age of death, as that age in which most people die, right? Usually, the life tables, they are estimated, calculated for age groups in the same way as we did for total fertility rate. The total fertility rate, we estimate age-specific fertility rates for women between 15 and 49, and we divided this age group, 15 to 49, in 7 groups of 5-year age group, 15 to 19, 20, 24, and so on. For mortality, we also do it by 5-year age groups, exactly because some countries might not have reliable information for single-year ages. We use it 5-year age groups. But we're going to see in the first age group, we usually break it on mortality of people with less than 1 year and people dying between ages 1 and 4, because mortality of people dying before reaching age 1 is higher than mortality of other children. So we break that age group in two groups, as we're going to see in the examples here. A life table starts with a population. So in this hypothetical population that we start, a life table is called radix. And we usually can say, oh, I have the age-specific mortality rates. So for all these age groups here, I have all these mortality rates for each one of them. And I expose a group of people to those rates. Let's say I assume that the radix is going to be 100,000 people being exposed to those mortality rates. And the idea is that that's the group of people that are born at that specific year in that specific country, and we experience those mortality rates. This number is arbitrary, but conventional. We usually use it 100,000, 1,000, or 1. It's not going to affect the final result of the life expectancy. It's just this exercise in which we get the mortality rates by age groups, and we expose this specific group of people to those rates. From each age to the next, the population is decremented according to age-specific mortality probabilities until all members die. So if we have 100,000 people born in a specific country, we expose them to the infant mortality, the mortality of people between 0 and 1 year of age. Those who survive are exposed to the mortality of those between 1 and 4. Those who survive are exposed to 5 to 9, and so on. The mortality schedule is fixed and does not change over the life of the population. It's that hypothetical exercise that we get this group of people here and expose to this mortality schedule, in other words, the mortality rates by age groups to this specific hypothetical group of people. So that's the example here. This example is shown in the textbook. That's the US population in 2010. So for the whole population in the US in that specific year, we get a series of mortality rates. The mortality rates are symbolized, as I mentioned before, by the capital MXN or by ASDR. That specific indicator is not here, but we get the mortality rates by age groups. Which age groups? Usually 5-year age group, but for the first one, we disaggregated for those who die before reaching age 1 and those who die between ages 1 and 4, 5 and 9, 10 and 14. So these are completed ages. Based on the mortality rates, how do I calculate the mortality rates for each one of the age groups? I calculate how many people died in a specific country, in a specific year, in that specific age group, and divide by the population in that specific age group in the middle of the period. And then I'm going to use a formula that translates the mortality rate into a mortality probability. The QXN is the mortality probability or probability of dying that I mentioned before. What's the difference between rate and probability? Rate, the denominator, the most correct information in the denominator of any rate, can be fertility, mortality, or migration, is person years. How many people lived overall across that year? One approximation to person years, the denominator uses the population in the middle of the period, the population in July 1st in the denominator. The denominator of a probability is the population in the beginning of the period. In this example here, the population that was below age 1 in January 1st, 2010 in the US, or the population between ages 1 and 4 in January 1st, 2010 in the US goes in the denominator of this formula of the probability. And if we get the mortality rate, we can use a formula that transforms it into probability, and we're going to see these formulas in the Excel spreadsheet that I'm going to show you. And then I said, okay, now we have the mortality probability for all ages here. And notice that for the last age group is 1, so it means that everybody dies. 1 is 100% of chance of dying. Right, here's the same thing of saying I have 0.6% of chance of dying, 27.4% of chance of dying, 78.3%, and so on. And then now I'm going to expose that hypothetical group of people to those chances of dying. And that's my next column, the little LX column. So this is the number of people who entered that specific age group. See here that the notation for Q has the QXN, because this is the mortality throughout that age group. This is the mortality between 1 and 4. This is the mortality between 5 and 9. Here we don't have the notation of N, because it's just saying 100,000 people were born in this exercise that I'm doing here. 99,388 people survived the chance of dying in the previous group and survived to age 1. This number of people here survived to age 5, to that exact age. So what we are doing here, out of these 100,000 people, they were exposed to this mortality here when they were babies. How many people died? If I have 100,000 people and have the chance of dying equal to 0.006, I multiply this one by this one, I have 612 people dying. So these are the number of people dying within that age group. The people enter that age group, the amount of people who enter is this amount here. They were exposed to this chance of dying throughout that age group, and that amount of people died. And again, the D is the number of people dying within that interval between ages 0 and 1, between ages 1 and 4 is here. So if I have 100,000 people who are born in the US in 2010, I expose them to this mortality. 612 die. How many will survive to the next age group? 100,000 minus 612 equals 99,388. I expose these people here of the chance of dying this new age group. This times this, 106. How many people survive to the next age group? 99,388 minus 106 equals this, 99,281. Okay? Until the last age group in which I have 1,000 people, 968 reaching age 100, and then everybody dies. I don't know exactly which age, but everybody dies. This number times this is 1,968. Okay? So here, I am pretty much saying that this exercise, the main thing is to use the mortality by age group. I start with mortality rate, the capital MXN, translate it into probability, which is the QXN. And in order to compare different populations in different years, I start with this hypothetical exercise. I expose this number of people here to these rates, and I have to do this for all different populations and years that I might have, and calculate how many people die in that age group. Out of these 100,000 people here, now it's good to calculate how many years on average those people live within that first age group. That first age group is just 1 year interval, right? From 0 to 1. from 0 to less than 1. Some people die, and I have an appropriate measure to do that, because in the case of infant mortality, usually when people die, they die more close to 0 than close to 1. But on average, out of these 100,000 people here, we had 99,465 person years lived. That if you get all these babies and sum up all the amount of years that they lived together, was 99,465. These people here, 99,388, is the amount of people who enter that interval. They enter the interval of 1 to 4. Some of them died. But now the number of person years, it can be if someone is alive at the beginning of the interval, is alive at 1, and continue alive until the end, how many person years that person will have lived? If I have one child that is alive at age 1 and survives all throughout that age group and survives up to age 4 and goes to the next age group, that person lived 4 person years. If I have a baby, a child that was alive at age 1 but died at age 3, that's at the end of age 3, that child was alive for 3 years, so that a baby or that child counts for 3 person years. For the next ones, it's the same idea. Someone who is alive in this age group here at 20. And if that person lives throughout all the interval here, from 20 to 24 and goes to the next, that person will count 5 person years in this column here. If that person dies right before reaching age 21, that person is going to count just 1 unit, 1 person year in this column here. So the capital LXN, or the big LXN, is going to count how many years this group of people who reached the beginning of the interval lived throughout that interval. Here is the number of people reached at the beginning, LX. Here, how many years overall those people live within that interval, big LXN. And I count this all here. Now, I'm going to say, okay, I want to know the overall number of years that this population lived for all these different age groups. So I will do a cumulative exercise from the bottom. I will get this number repeated here. 29,000 is the result of 24 plus 4,000. This 108,000 is 79 plus 24 plus 4, until we reach here 7.8 thousand. It's the sum of all these rows here. So what does the big TX tells me? It tells me the overall number of years that this population would live if they were exposed to these mortality probabilities throughout these age groups. So let me simplify the example. Let's say that we have a population in which only 2 people were born. Only 2 people. Only 2 people who were born. One person lived until age 70. The other person lived until age 72. How many years in total those 2 people lived? Can someone write in the chat? Can you guys answer? Have 2 people. One lived up to age 70, and the other one lived up to the age 72. How many years overall they lived? 142, right? In this simplified exercise, the 2 people are the same as this number. The 142 is the same as this number. So I have one person who was alive until age 70, the other one 72. Add them, 142 is this number here. How many years on average these two people in my simple example lived? 70 plus 72, 142. Divided by two people, 71. Right? So 71 is how many years on average they live. How do we do this in the life table? Same thing. I get the overall number of years that they lived all together, 7,866,027 years, divide by 100,000, 78.7. Right? And so that's what the life expectancy at birth. See, it's just the EX, doesn't have the N either. So that's for the first group, is the E0, as I mentioned before. So if we have a hypothetical group of people and expose them to these mortality probabilities, they will live on average 78.7 years. Let's say that someone did not die in earlier ages, and that person lived until at least age 50. If someone lives up to age 50, that person was exposed to the chance of dying in previous ages, but did not die, survived. That person is still here. Still here. If that person is still here and he survived up to age 50, what's the life expectancy of that person at age 50? We look at this number also in the last column, 31.4. So that's the life expectancy at age 50. What's the symbol for this one? It's E50. It means that if someone reaches up to age 50, based on this data, that person will have an additional 31.4 years of life, which means that we would expect that person to live on average until age 81.4. Right? 31.4 here, plus 50, 81.4. 81.4 is greater than 78.7. Why? Because that person was exposed to the chance of dying in previous years and didn't. It survived. So it overcame all the risks, and then that person gained some bonus lives, bonus years of life. That's the idea, right? So that's the life expectancy, that's the life table in which we calculate life expectancy at birth and life expectancy at all these other age groups. So in these next slides, I will just pass through in detail about these columns, and then I'm going to show you how to exactly calculate those in by hand, or I'm going to show in Excel specifically. Translating the mortality rate, the MXN into the QXN, we need a more specific formula. The LX here is easy to calculate. We just multiply this. We just get this number minus this, we get this number minus this, we get the next, and so on. The number of people dying is easy as well. Just multiply this by this. The big LXN, we also need special formulas because in specific cases, like in the first two age groups here, children are more likely to die at the beginning of the interval. They're not likely to die in similar ways throughout that interval. But the big TX is also simple. It's just a cumulative count going from the bottom. And the life expectancy is just this number divided by this number. Okay? Once you reach the beginning of the interval, how many years you will live after you reach that age group? So this number divided by this number, we get this. So basic life tables columns, the age intervals of each group, which is the first one here. The second column is the probability of dying between age X and age X plus N. LX is the number of survivors at age X, at the beginning of the interval. DXN is the number of deaths between age X and age X plus N. So these symbols matter. It's probability of dying in the interval. So that's why we have XN. Number of people survive at the beginning of the interval. That's why we just have X. Number of people dying in the interval. That's why we have XN. Number of years lived by all persons who enter the age interval while in the age intervals, the big LXN. The big TX, number of years lived by the population in the age interval and in all subsequent intervals, and the EX, remaining life expectancy at each age. Once I reach that specific age, how many years should I expect to live from then on? Okay? So age groups refer to the range of years between two birthdays. The age group 5 to 9 refers to the 5-year interval between the 5th and the 10th birthday. So here we include only people with completed ages, people who completed 5, 6, 7, 8, or 9 years of age. Those that are like died at 9 years and 11 months of age, those people enter here. Those people that just completed their birthday, their 10th birthday and die, they enter the next one, 10 to 14. Okay? Really bad talking here, but of mortality of children dying. It's crazy, I know. It's bad. So the probabilities of dying, QXN, is the most basic column of the life table, and shows the probability of dying for each age group. These are probabilities that persons alive at the beginning of an age interval will die during the interval before they reach the start of the next interval. We can have here the probability of dying equals the number of people who died in that specific age group divided by the number of people who survived to the beginning of the age group. But the way that we did in the life table, we got the mortality rate, the MXN, translated into the QXN, and then afterwards, we get the L column, the red X, the 100,000 people, and then we estimate the number of people dying in the interval. Because little LX is here dividing, it just goes to the other side multiplying. So DXN equals QXN multiplied by LX. That's exactly the examples that I showed you here. 99,388 multiplied by 0.001071 equals 106. And that comes from this formula. And for the last age group, the probability of dying equals 1, as we saw before. And of course, some life tables in some countries, we don't have so refined information of mortality to older groups. We can have only up to, for example, 80 plus or 85 plus. The difference between the mortality rates, the MXN, and the mortality probabilities is the denominator. Remember, rates, the denominator is the number of person years. We saw before that an approximation to that is the population in the middle of the year. The probability of dying, in this case here, the denominator is the population alive at the beginning of the age interval. Why that? Why do we need the probability? Because this LX is the number of people at the beginning of the age group. So we have to expose these people here at the beginning of the age group throughout this mortality within the age group. So we need the probability. not the rate. We need the probability because we're going to multiply this by the population at the beginning of the age group, not the population in the middle. Okay? That's the main reason for that. Next column, the number of survivors, number of people alive at the beginning of the age interval, known as the little L column. So that's actually called by demographers like that, the little L column. It is calculated by subtracting the number of people dying from the LX value in the age interval immediately preceding the one being calculated. So of the 99,224 people alive at the beginning of the age interval 10 to 14, 70 will die throughout that interval, and then 99,154 will be alive at the beginning of the next one at age 15. So 99,224 minus 70, this number minus this is here. In the life table, just go back to the life table. What we're calculating is this number here. 99,154 equals this minus this. Okay? Cool. The number of deaths, number of people who died during a particular interval throughout that interval, and we just use the same formula that we had for the probability. So we go for the formula for the probability here. Little LX is divided, we just go to the other side multiplying, and that's what we get here. For the number of people who died during the age interval 40 to 44, how we calculate it, we have the probability of dying equals to 0.009979, and the number of people alive at the beginning of the age group. So 966 will die. If you go back to the life table, we did this exercise here. For 966 is the probability of dying multiplied by the number of people who reach exactly age 40 at the beginning of the interval. Okay? Next, years lived in the age interval, the big L column, also the way that's known by demographers. The total number of years lived by all persons who entered that age interval while in the age interval. So the example, 98,011 persons are alive at the beginning of the age interval 30 to 34. So 98,011 reach exactly age 30. If none of them died during the age interval, they all would have lived 455 years. How did I get into this number? I just get 98,011 multiplied by 5 because we have 5 years there from 30 to 34. But we know that 539 of them died and we have to discount. So if you go back, we're talking about the group 30 to 34. Here, if all these people who were 30 years old were alive at age 35, means that nobody died here. 0 people died here. So the big LX column, LXN column would be 98,011 multiplied by 5, and then we would have those 490. But since we have this death here, we have to subtract that, right? And we have specific formulas that I'm going to show it to you. And there are different formulas for the big L column. Demographers usually assume that deaths are roughly distributed during the 5-year period for many of the age intervals. So usually for the age intervals 20, for example, to 24, we assume that people die with the same chances from 20 to 24. From 25 to 29, we assume that mortality is at the same level within that age group. However, the assumption does not apply to the first few age groups. So there are several formulas to produce the big L column value for the first few age groups. Different demographers use different formulas, and I'm going to show some of them in the Excel file. So what is the thing is that for babies that born before reaching age 1, the ones that die before reaching age 1, they are more likely to die closer to age 0 than to age 1. So we have a specific formula for that. Children that born between the ages of 1 and 4 usually die closer to age 1 than to age 4. Okay? And we also needed another formula to the last age group. In that case, in that example, for the 100 plus age group, because we don't know how many years those people are living all throughout their lives after that. So we have to come up with a cap, okay? And in the examples, I'm going to show specifically that. The years lived in current and subsequent age intervals are pretty much the cumulative result coming from the bottom to the top of the big L column gives us the big T X column. So the formula is simple here. It's the total number of years lived by the population in the age interval and in all subsequent ones, subsequent age intervals. We sum the big L column from the oldest age backwards, so from the bottom to the top. So from a specific age group here, we start summing the big L column from that age group until the last, right? So if you have the T50, we're gonna add the big L comes from the age 50. So the I here goes from 50 until the last one, until the last entry in the life table, which is symbolized by the W here. Cool? Example. If someone, like how many years on average, how many years in total people lived in the US in 2010 if they experienced those mortality rates after age 95. How do we calculate that? We pretty much just add up the last two big L numbers. 24,000 plus 4,000, 29,000. So I'm just getting here, since I'm getting the cumulative value from here into the bottom, it's just this number plus this number. This one is this, plus this, plus this, as I mentioned before. And then, finally, the remaining life expectancy. Average number of years of life remaining at the beginning of the age interval. So if someone reaches the beginning of a specific age interval, how many years on average they will live after that? It's here, how many years on average divided by the number of people gives you the average number of years expected to live by those people. Life expectancy at birth is the big T0 divided by the little L0. Life expectancy at birth 25, big T25 divided by L25. Go back to the life table. So here I'm saying, these people here were born, so they all were 0 in this population. And overall, they lived all these person years. If we add them all, equals this. This divided by this, 78.7 years on average. What was the other one? Was 20? If I have 98,910 people reaching age 20, they will live on average all this amount of person years here. Or they will live all these person years here. If I add them all, I get this total number of person years. Total number of person years divided by the number at the beginning of the interval, I get 59.9.5 years on average after they reach age 20. So it will be 20 plus 59 is 79.5, which is higher than the original one because they overcame some risks of dying. And one column that's not shown in the table and which I just made the calculation now, is the average age at death. The life expectancy is the expectation of future life beyond age X, is not an average age at death. We add X, which is the age at the beginning of the interval, and EX to obtain the average age at death for cohort members who survived that specific age group. Not all life tables include this last column, X plus EX. And this X plus EX column always goes up, because once we overcome the chance of dying in previous ages, we have a bonus, some bonus years of life to live. But at the same time, the EX does not always go down. It often goes up after the first years of life, because babies who survive infancy are no longer subject to the high risks of infancy. But infant mortality rates in the US is so low that it does not go up in our exercise here. It does decrease from 78.7 to 78.1. But some countries you might see the life expectancy going up here, exactly because you have so high probabilities of dying during infancy. But overall, so if I get this number here, 40.5 plus 40, I'm saying if people survive up to age 40, you would expect them to live until around age 80.5, 40.5 plus 40. If people survive up to age 45 exposed to this mortality rate, we expect them to live up to age 80.9, right? So we get some bonus years of life here as we survive the chance of dying in previous years, previous age groups. And that's the XN column. These are the typical shapes of the life functions. The probability of dying is usually higher in the first age groups and then go down. And then afterwards starts to go up until it reaches really high levels in older age groups, and it equals to 1 in the last age group in our life table. Number of people dying is usually high among infants before they reach age 1, and then because a probability of dying declines, number of people also decline, and then start to increase until reach really high levels. But although we know their ages, the probability of dying are high, not as many people are alive there anymore. So the overall number of people here dying declines. They have higher chance of dying, but the overall number of people declines because we have fewer people alive in those older ages. The overall number of people alive at exactly that age starts at 1. In our example there in the life table was 100,000. And then as people start to die here, the number of people alive goes down until everybody dies. And the life expectancy, in some cases, you can see an increase in life expectancy from life expectancy 0 to life expectancy 1. That was not the case of our example, but then afterwards starts to decline. But you have to remember that you have to get this value here, add to this number in order to have the average number of years that someone who reaches age 60 is expected to live up to. And this table, these figures here, I got it from another textbook, Wachter, and that's the same textbook that I used before to talk about some methods in demography throughout the semester. And this textbook, you can see the reference at the end of these slides, is available for free for you here in electronic format in the library. And these life tables are also really useful for us because it allows us to do some projections of population. So Alfred Lotka used life tables in the development of his stable population theory. His main argument was like, so populations, we saw in the demographic transition theory that mortality declines, and then afterwards fertility starts to decline. And after some decades, some centuries, those levels, they vary, but they are really, really low, mortality and fertility levels. Let's say that a specific population keeps with those really low levels of fertility and mortality, and they don't change much. They kind of like stay constant over time, the fertility and mortality levels by age group. And let's say that that population doesn't have many immigrants, people getting out of that country, or immigrants, people getting into that country. So what he, in his model, what he shows is that if a population who does not experience migration experiences constant age-specific fertility and mortality rates, that population will develop a constant age distribution. So we can, if a population is not changing mortality and fertility that much, we can expect that after some decades, if they continue with those levels of fertility and mortality, the age distribution will reach a specific shape. That population will grow at a constant rate irrespective to its initial age distribution. And remember, whenever we are talking about this hypothetical exercise in demography in UCL, we are talking about a closed population. What does it mean, a closed population? We are saying that that population might experience some changes in mortality and fertility, but I'm not taking into account migration. I'm not taking into account immigration or immigration, only fertility and mortality. And in this case here, I'm going beyond. I'm saying, let's say that the mortality and fertility rates do not change too much over time. If they continue in those levels for a long time, age distribution will tend to be constant. And stable populations can have either positive population growth or negative. If you have more births than deaths, population increases. If you have more deaths than births, population decreases. And if, I didn't show here in this slide, and if population have the same number of births and deaths, we have population that doesn't increase or decrease in size. That population in which the number of people being born and dying is similar in a specific year is called a stationary population. Stationary population is a specific case of a stable population. Stable population, we have kind of constant fertility and mortality rates. I'm not taking into account migration. But in that case, if fertility is higher, if number of people being born in a country is higher than the number of people dying, we have a positive population growth. If more people die, negative population growth. If the same number of people being born and dying, then we don't have any population growth. We have a stationary population. Again, stationary population is one kind of a stable population. The next slides here are kind of like some more explanation about life tables, so I consider this as being extra. And in this case here, example from another textbook of life table of US women in 2010. Usually we do these calculations of life expectancy by sex because mortality varies a lot by age, but also by sex. And you see here in this life table, it does show the population in those age groups in the middle of the period, the number of women dying throughout that period, this number divided by this number is the age-specific death rates, and we transform the death rates into the probabilities. In the previous example that I showed, the life table was starting from here. So that's just the same idea. And the interesting thing about the life table is that after you get the result of the life table, this case here is for the US, 2007, female and male. if you get this column here of the big LXN, you can apply that model of Loftka. Let's say that mortality rates are not changing much, are going to be stable like this for women and for men. And the overall number of births is going to be similar. We expect that this population will have this age distribution here. We can get these numbers here, these two, translate them in percentage terms, and then we get this population. So what is exactly this? What is the real population in the US in 2007? Where do I get it from? From this column here, population by age and by sex. This column. If I get these two columns, translate them in percentage, I get this age-sex structure. If I get this one here, this is the population that I would expect if the mortality rate stays stable over time. I have pretty much the same number of people being born, and I don't have migration, closed population. I get these columns, put them in percentage terms, I get this. Okay? And this is the age structure, age-sex structure of the US population if mortality and fertility did not change much after 2007. So these are just more. And when you unzip the file that it's on the mortality chapter in the course website, one of the files will be this estimation here of the US mortality life expectancy with data in 2007, using data from the American Community Survey, population data from the American Community Survey, and death data from the CDC. So when you unzip the file, you have the standardization results that I showed you for US and Venezuela in the previous class. And for life table, you have both the one based on this method by Kintner and the one by Wachter. The one by Wachter is the one that I prefer. Is a textbook that you guys have here for free. You can download and have in PDF in your computer. And that's the one that I have open here. And for this case, I actually got data up to 2017. So in the lecture here, this one here is 2007, but it's the one that I used for this exercise, this 2007 here. For this one, I got data more recent, 2017. In 2014 is just the year that the book by Wachter was published. But here, I pretty much went into the CDC website, this website here, and collected information of number of deaths and population by age group and by sex, women and men. Population in their case, it goes only to 80 plus. It does not break down for older ones. So these ones here, these deaths, I added them all and I put them in the 80 plus group, right? So I just got this raw data and organized it. And I did it 80 plus. So this data here is pretty much the data that I got from the CDC in 2017 for women and men, deaths, and population. Here I calculate a life table for women, life table for men. For women, I get these two columns. For men, I get these two columns. For women, I have here the population by age group and the number of deaths. So 1.9 million, 9,800. It's exactly those numbers here. 1.924. 1.924 and 9,867, exactly this number. And then, I'm just going to close the chat here, just hard to see. And then I have the age groups, the age at the beginning of the age group that I'm going to use at the end, the width, how many years in each one of these age groups. This one is only people dying below age 1, so just 1. Width, 4 ages, 5, and then infinity. And the average years in the interval, that's going to be important for us to calculate the big LX and column, is the first exercise that applies some formulas. All these formulas here in the bottom come from the textbook of Wachter, which is the one that you can download it. For the first age group, the age group of those coming below age 1, we apply this formula here for the average number of years that people are living in the interval. So 0.1. So people who die between ages 0 and 1, they die closer to 0 than to 1. Okay? People who die between the ages 1 and 4, they die closer to age 1 than to age 4. So the average years in the interval is 1.5 only. And here 0.1 is not 0.9. When they die closer to 0. When they die closer to 1. And in this order here, it's just saying that on average, people die around 2.5 years within that age group. So from 10 to 14, I will live, so 5 years, I will live on average 2.5 years. And these formulas are from here. The first one is exactly this formula, using the mortality rate from here. For 1 to 4, it's pretty much this constant, 1.5. And for the other ones, is the width divided by 2. This is the raw data that we calculated before. This number divided by this number is the mortality rate. And this mortality rate here is used for this one. The mortality probability. So the mortality rate is the number of deaths divided by the population in that specific time. To calculate the mortality probability, we implement this formula here. So that's the transformation from a rate to a probability. We get information on the width, the mortality rate, and the average years in the interval. And these formulas can vary from textbook to textbook. So this is just the implementation of that formula. So C4 here is the N. G4 is the mortality rate, is here on G, divided by 1 plus N, again, is the C4, minus AXN is the D4, times the mortality rate, again, G4. So that's how we calculate those. And at the last one, equals 1. There is no formula here. For these other ones, we have the same formula, right? These people are alive. If we get this times this, we get the number of people dying. This is what I can estimate as being 1 minus the probability of dying times this. 1 minus probability of dying is what? Probability of surviving. So there are different ways to calculate the L. It can be 1 minus the probability of dying times the previous LX, or it can be the L minus the D. So 99,490. If I just get this number minus this number, I get exactly the same value, right? Until the last one in which everybody dies. The big LX and column uses information of people who are, for example, here in the big LX and column. Those people here that survive to the next age group. So let's take this one and this one. These people here who survived to the next age group survived all 5 years. So they get the next little lx and x plus n multiplied by 5. Because they survived all the 5 years in this age group and went here. So this number times 5 is how much they will contribute to here. And how many the remaining people did. These guys here. These people died. How many years on average they live? 2.5. Right? So these people here, 53, lived on average 2.5 years. 53 plus 2 times 2.5, they will be contributed to this term here. These guys survived to the next one. So they lived 5 years in the previous one. 5 times this, they will be added here. So that's the formula. The C times the next ones that survived the previous, plus the D times the one who died here. Right? And the last LX column, big L column, is pretty much the how did I do here? Sorry. Is the average years in the interval, 4.8, multiplied by the DXN. It's just a way to make everybody die in the last interval, but there are different formulas here as well for this last cell. All these formulas here are for this last cell. I could simply get this number and divide by this number, I get this. And then the big T is just a cumulative from that row to the bottom, that row to the bottom, and so on. The life expectancy, this divided by that, this divided by that, and the average age at death is just this, plus the age at the beginning of the interval. So someone who survived up to age 25, we expect that person to live up to age 78.7. So we got some additional bonus life here. And this is just another way to calculate, to just make an exercise here to see if everything was correctly calculated. So this column here is just similar to the original column. It's just checking if everything was calculated correctly. Okay, so that was the class about life table. The quiz, the next quiz is available now, and it's going to be available until tomorrow at noon. But the quiz today does not cover life table. It covers the other parts that we cover in the mortality chapter. Introduction, measurement, and standardization. Okay? So thank you very much. And I see you guys on Thursday. Okay. Thank you.